Hello, this is Curtis Eckerman, and I want to walk through an example of the standard deviation and how to calculate that. But before I do so, I wanted to also demonstrate what a standard deviation number tells us, and I want to do that through this graph. I've used some formulation in Excel to kind of reverse engineer a standard deviation graph, and we're going to assume in this example that this is a test grade. So imagine I've got a lot of students taking a test, and there's an average to that test. I think we can all relate to that. So in this case, I've set the mean or the average of the test at 70. I could set this mean at anything I wanted to, for instance, and it'll move it. But we're going to start with 70. That's a pretty reasonable average. And right now, the standard deviation is 1. Well, what does that mean? In the lab, I have described standard deviation as a description of how far the data varies from the mean. Basically, it's looking at the dispersal of the data around a mean. So in this case, a standard deviation of 1 means that the standard deviation is 1 point away from the mean. Well, that doesn't mean that all the tests are only 1 point away from the mean. Instead, it is a distribution description suggesting that around 68% of the data is within 1 point of the mean. So in this case, it means that it's roughly 68% of the data should be between a 69 and a 71. Okay, and so if that standard deviation changes, then it means that the data is more distributed. So 2 standard deviations, or 2 points, would represent around 95% of the data, right? And so it's actually, I think 94 actually, or 90. It's actually 96%, but we'll go with 95% because it's not exactly 96. But so 2 standard deviations would represent roughly 95% of all of that data, and I'll show you that here in a moment. But I want to give you an idea by changing the standard deviations and seeing what happens to our graph. So let's say instead of a standard deviation of 1, because that's telling us right now that almost all of the tests are really close to 70%. Okay, but let's imagine a standard deviation of, say, 5. And you can see what happened is now I have the same mean. I've used the red dashed line here to represent the mean. The mean is the same. Most of the data clusters around the mean, but now the tests are more variable. There's more high grades and there's more low grades. And so now this data is more dispersed around the mean, or it's further distributed around the mean. So I'm going to use another standard deviation of 10. This is going to be an even more dispersed mean. Now it's getting more jagged too because of the fact that I have 2,000 points in this particular data, and as a histogram I'd need more. The more points I added to it, it'd smooth out. But you get the idea. There's a general curve here. Some people refer to this as the bell curve of grades. I'm going to drag this little box down here, and I'm going to show you first of all a standard deviation of 10. So that means a standard deviation of 10, 68% of the values fall between 60 and 80. So something along these lines right there. And so I'm going to make this box bigger. Basically, we're saying that in this box, roughly 68% of the data falls between these two values. And you can see, look at the data here. Most of the numbers fall here. Now, 2 standard deviations. Sorry about that. Didn't mean to move the graph. I wanted to move this box instead. 2 standard deviations means that we're looking at the data between 50 and 90. So let's do that. Let's draw this box. And so in the darker yellow box, that represents roughly 68% of the data. In the bigger box, that represents around 95% of the data. So there's still some data outside of that, but you now see what we're doing. We're describing the distribution of the data by using standard deviations. And so even with the same mean, we can, if I have a standard deviation of 1 versus a standard deviation of 10, I have the same average, but clearly the data are different. And just to remind you, if I go back to 1 right? That's clearly a different outcome. So my boxes, I would have to reshape my boxes much differently. They'd have to shrink quite a bit. So this would be between 69 and 71, something like this. And 2 standard deviations would be between 68 and 72. So let me, didn't mean to change the graph there, but let's see if we can make this box a lot smaller. You get the point. So there's my 2 standard deviations. Instead, these boxes are much tighter. So that's what standard deviation means. And so in calculating standard deviation, we are going to be looking at each data point and how much it deviates from the average. We're going to be taking this, let me change this again. We're going to be taking every data point. Let's say there's a data point out here. We're going to be measuring how far away it is from the average, and we're going to be looking at the average of how far these things differentiate. So let's go and look at the data that is I gave you in the example in the lab. And this is from a shorebird, a seabird. This is metabolic rates measured in calories per day, and this is the data that's given you. And so this is the female data here. As you can see, this is the female data, and this is something that you would have measured. So this is female 1, and this female has a measurement of 727.7 calories per day of their metabolic rate. And that's the kind of experimental data that you would have to measure out in the field or in the lab or something along those lines. There are 6 data points here, and so that's why the n is equal to 6. And the very first thing we would do before we get to this, and I leave the reference of the standard deviation calculation down here. This looks complicated, but we're going to work through it. The first thing we're going to do is make an average. We're going to average these numbers. Okay, and you can do this with a calculator. If you're doing this in Excel, it's pretty easy as well. I'm going to create a formula. Formulas always start with an equal sign, and I'm going to average by selecting these numbers and create an average, and it's going to be 1,285.5. I'm going to that's too many digits. I don't need them to be. Here we go. I'm going to reduce this, so I'm going to leave it at 1,285.5. Okay, the next thing we're going to do, well, let's look down here in the standard deviation equation for a moment. Notice that what I'm going to do is I'm going to sum, and that's the sigma symbol here. This is a sum from I to n. I represents each individual sample. For every individual, I'm going to take that individual calculation. I'm going to subtract the average. So for instance, in sample 1, this is x sub 1. This is the I sample. And then we're going to subtract the mean. So we're going to put this mean into every cell here, because we're going to then use it to subtract. I'm just going to copy it down. I've just copied the mean. So here's the mean. I've just put it here. We're going to subtract this mean from this sample. And so that's what's happening right here. We're subtracting the mean from each sample. And then we're going to sum all those. But before we sum all those, we're going to square them as well. But let's just deal with the subtraction first. And all we're going to do is we're going to subtract this number from this number. And to do that with Excel, you can again do this in a calculator or by hand. I'm going to take this number and I'm going to subtract this number, and it's referencing the cells C4 minus D4. I'm going to get some negative numbers. That's fine. We don't worry about negative or positive numbers. Roughly half of them will be positive and half of them will be negative. And that's always the way it works out here around a mean. Okay, so I've got these numbers. These don't mean anything to us yet, because then what we need to do is we need to square them. And squaring them, it's always a little odd when you see the fact that part of this equation is squared and then we take the square root. Well, if you know anything about math, if I square a number and then I take the square root of it, then I get the same number I started with. So 2 squared, square root of that is just 2. But there's a good reason for doing that, and I explain it in the lab a little bit. But part of the reason for doing that is that if I didn't square the numbers, 1, I would end up with negative numbers, and 2, those numbers that are really far away from the average, we want to exaggerate those numbers, and that's what squaring does. So that's a longer explanation, but just to do it mechanically, we just square this number. So in Excel, again, you can do this with a calculator, you can do this by hand. We're going to square this number. I don't recommend doing it by hand because it takes a long time, but I'm going to square this number. I'm going to take this negative number, and in Excel, use this hatch character, and I used a 2, and that squares it. So that's what happens, and I can just copy this down because it'll do that for each one. It's going to square this number, this one squares this number, and so forth. Okay, so I've squared, I have subtracted each individual number here. I've subtracted the mean from it. That's what I got here. Then I squared it, and now I need the sum. So I've collected all of the xi minus average squared. Now I need to sum them. And to sum them, I'm just going to sum them, add them all up. I'm going to add all of these up, and I've got this number. So I've got this big number here, 886,047.09. And so that's a number I'm looking for, and that's the number that's going to go in the top part of the equation. So I am going to, and I can now start plugging in numbers, because n, we know what n is. It's 6. It's going to be n minus 1. It's going to be this number divided by 5. So I'm going to do this as an equation. I'm going to do this number here, and I'll just type it out, 886,047.09 divided by 5. Okay, we get that number. Well, we're not done. We have to take the square root of this number as well. So I can go back and edit this equation, or I can simply do this as well. Square root, I could take the square root of 177,209.418, and there's my number. So 420.96. That's actually my standard deviation. So my average, right, and try to make sure that this makes sense. My average is 1,285.5, and then it's plus or minus 420 point, well, I'm just going to say 421.0 here. And so this is my average, and this is my standard deviation. So we're saying, as per our conversation on the previous tab here, we're saying that this is the average number, and this is how much it varies from the mean, right? And see if that makes a little bit of sense. We need to have data points that are varying from that point that much, right? So if 1,285 is my average, look at this number, for instance. It does vary quite a bit from that. That's about 550 away from the average, for instance. This one is only, this data point is only, looks like about 200 away from the data point. So it's within that standard deviation. So that number seems to make sense. That's all we're trying to get. We're trying to get an average and a standard deviation, because then that describes this population's average metabolic rate and tells me something about its distribution. That's the power of the standard deviation and why we need it. If this standard deviation, for instance, instead was 10, if that was our number, then clearly that tells us something very different. It tells us, in this case, it would tell us that the average is very narrow. That is, that almost all females have the same metabolic rates per day. And so clearly that's not the case with our number of 420, because that's much more variable. Okay, that's how you calculate a standard deviation. That's why we need it, and that's how we use it, and that's why the number has meaning, because it tells us something about the variation of the data around the mean. Okay, I hope that helped, and look for other future videos to help you with questions like this.